At the beginning of the 1900s, Max Planck came up with a way to explain the process by which a black body emits energy, since at that time classical theory led to what was known as the ultraviolet catastrophe. This was an interesting physical phenomenon which at that time was essentially a paradox, and to put it very simply, was based on the idea that at some point the emission of energy becomes infinite. Max Planck refined the mathematical logic and said that energy should not be considered as a continuous flow of something, but rather as a quantized flow of these related entities. A little later, the young Einstein, picking up on this logic of dividing energy into packets and using this approach, explains the photoelectric effect. The article on the photoelectric effect makes Einstein one of the most recognizable physicists of that time, and in a way shapes his scientific reputation. As you have already understood, we are talking about the formation of quantum physics, and a little later, a full-fledged mathematical formalism appears, which in fact, using the idea of this packetization, forms a new perspective on the nature of the world, creates a new physical picture, and establishes a new physical approach. But the cruel irony is that at first Einstein used this logic and successfully explained the photoelectric effect, and a little later Einstein proposed the theory of gravity and worked on the theory of relativity. Well, all of this contradicts quantum physics, and we become witnesses to the emergence of a deep contradiction that cannot simply be resolved between the two schools of physics or between the two approaches. It turned out that quantum physics works on one side, while Einsteinian physics, let's call it that, or physics that is more similar to classical physics, works on the other side. Thus, Einstein himself, understanding this problem along with other prominent scientists, began to develop the so-called theory of Grand Unification, or the theory of everything. And in fact, it is the theory of everything that we are discussing with you today. When you start thinking about this problem, for some reason a childhood joke immediately comes to mind, which you have probably heard. It seems it's either about Chekhov or about some other writer. With one foot he stood in the future, with the other foot he stood in the past, and in between was the harsh reality. This is roughly how the picture of the world is formed in modern physics. We have quantum physics as a separate field, and we have classical physics, or Einsteinian physics, as another. And these two types of physics often do not correspond to each other. Quantum physics quite successfully explains phenomena that could not be explained by classical physics. And on the other hand, there is a slightly different problem. On the other hand, there is classical physics and Einsteinian physics. Einsteinian physics assumes that there is no quantization and that we have, well, as we've mentioned many times, gravity is a consequence of the distortion of space-time. With this approach, quantization is impossible. And why is it impossible? Because if we are going to quantize gravity, then we have to find the hypothetical graviton. And, as is well known, we have not been able to find the graviton so far. Nevertheless, all quantum logic is based on the idea that whatever happens around us, it happens because of the tiniest pieces of something. If we consider some physical phenomenon then, for example in material science, the tiniest particles always play a role. In the case of some field, it is necessarily the quanta of the field that operate in this way. But Einstein's physics does not assume this. In other words, we have two completely opposite approaches which overlap in some ways, but in others are in strong conflict. And this conflict at the moment turns out to be essentially irresolvable. And probably the most striking contradiction that can be highlighted between Einstein's physics and quantum physics is the possibility and existence of a probabilistic approach. At first, quantum physics seems completely insane, because everything that happens there is described in terms of probabilities. We never have a particle, the particle has no definite position, we never have anything at all that can actually exist. And we describe all of this using the so-called wave function. On top of this wave function, there are quirks like Heisenberg's uncertainty principle, and this uncertainty means something very simple. We cannot simultaneously measure both the position and the velocity or momentum of a particle. And this set of completely incomprehensible and unconventional views fundamentally contradicts classical physics. And so, in Einstein's physics or classical physics, we simply cannot imagine a situation where, say, there's a lamp sitting on top of a wardrobe and its position is probabilistic right now. Or rather, can we? If we dig deep enough, we could probably approach this lamp as a certain interaction of many quantum particles. Each particle will have its most probable specific position, and this most probable position will coincide with the positions of the other particles. All these particles together form the lamp. And yes, in that case, this logic would work. But that's delving too deep. It's partly hypothetical, and this perspective isn't always appropriate. So what perspective is appropriate? The appropriate perspective is that in classical physics, we have a classical approach. We have absolute space, Newtonian space, and we have absolute objects. And all this probabilistic mess, let's say, belongs more to the realm of quantum physics. Quantum physics assumes that some processes can occur instantaneously. It also assumes that the principle of locality can be violated. It even assumes that the principle of causality itself can be violated. And the whole world is viewed, let's say, in a different light. There is no time there, no continuity, nothing of what we are used to seeing around us in classical physics. And then it would make sense to have some kind of standard theory that unites all these perspectives. And then we could say, well, it's not a big deal, since we have some standard theory that can explain all of this. And yes, then we wouldn't need to use these two fundamentally separate approaches. We don't need quantum physics and we don't need classical physics, we have something in between. The true meaning of the Grand Unified Theory is that we need to unite the two schools of physics and somehow arrive at a single system that describes both types of phenomena equally well. By the way, you might be interested to know that in some sources, the theory of everything is described not as an attempt to reconcile quantum physics and Einsteinian physics, but simply as a new perspective on, let's say, the development and description of the system. According to this view, the theory of everything includes all four fundamental interactions, which are unified by a single equation. And with such an equation, these interactions can describe absolutely any process occurring in our universe. And this logic has the right to exist if, let's say, it were possible to fit everything into it. But as you remember, that problem also appears there, and it's still impossible to fit gravity in. That's why this universal equation, which could supposedly solve everything, runs into the same problem as the theory of everything. I'm telling you this because in some cases you might come across a description of the theory of everything or the Grand Unified Theory as, let's say, some kind of universal model capable of solving any problem with a single equation. And here, quite a large number of theories emerge that try, so to speak, to combine bread and butter, and attempt in some way to connect quantum theory with Einstein's theory. For example, one of the most popular theories is string theory. Here, well, there's probably no point in delving into it too deeply, but the logic is based on the idea that all interactions in nature are built on the existence of the tiniest strings, which, so to speak, connect energy centers. Well, that's how I imagine and understand this theory. Perhaps it's more complex or, on the contrary, simpler. String theory, at the same time, implies the existence of a huge number of dimensions, and this number of dimensions suggests that in this multidimensionality, there can exist all sorts of interactions, including those that we cannot perceive in any way. And since we can't see or sense them while living in three-dimensional space, in 3+1 space, these strange and complex intertwinings can in many ways explain the phenomena that we observe. Particles in string theory are replaced, let's say, by the concentration of vibrations of the corresponding thread, the corresponding string, and all interactions between particles are explained through the transmission of interactions along these strings. The theory seems very logical, the theory seems quite correct, but as far as I know, modern physics regards it, let's say, rather indifferently. Nevertheless, there have been many attempts to reconcile the logic of the two great theories, and among them, string theory is probably one of the most well known, because from there, you can dive into all these attempts to describe gravity in all sorts of different ways. You can delve into efforts to reconcile all of this with quantum theory. And there, as they say, it's a complete mess. There's no telling what you might find. That's why string theory is probably one of the most authoritative in this area. And perhaps the only rational question you have left is this: why do you believe that a theory of everything does not exist? Why do you think that, at this point, all the developments we have are, let's say, incorrect, mistaken, or, let's put the question differently, what should be the criterion for the emergence of a successful theory of everything? And the only criterion for the emergence of a successful theory of everything should be the presence of a mathematical formalism. Yes, unfortunately, all the theories we're talking about are based on mathematics. And perhaps the word unfortunately isn't entirely appropriate here, but there's actually not that much physics in these theories. For the most part, any approach was worked out mathematically before it appeared and before it found any confirmation. Everything we're talking about right now is purely a mathematical approach. And this mathematical approach implies that any theory exists first on paper, and then, under certain conditions, it becomes possible to observe it. As I mentioned in the video about the speed of gravity, for the most part, the very idea of gravitational waves initially existed only on paper, and only later was this idea discovered, confirmed, and the existence of gravitational waves recorded. And this kind of approach leaves its mark. Therefore, in fact, the confirmation of the existence of a theory of everything, or rather the criterion for the truth of an emerging theory of everything, should not be a mathematically self-consistent formalism. Unfortunately, and why unfortunately? Because with this approach, there isn't actually that much physics left in the theory. After all, you have to agree, just because something works out mathematically doesn't necessarily mean it will work out physically. Although, to be fair, I have nothing against mathematical physics. And the examples I just gave are, by and large, a successful way of confirming that so-called mathematical physics works, and most likely, will continue to work. All of this is constructed as a kind of algorithm. I've talked about this many times already and have shared my thoughts with you. And since it works in roughly this way, mathematical logic can have its place. But wherever the strengths of such logic appear, its weaknesses also become evident. The point is that we can consider these models to be incomplete, and the theory of everything might not align. Not because we lack some unified school or a common approach, but simply because we are building the basic mathematics incorrectly. With this approach, it may turn out that the very distinction between quantum and classical physics has no place at all. Therefore, probably the first stage in the success of developing a grand unified theory will be the ability to reconcile the mathematical formalisms of these two different approaches. Of course, later on, it would be desirable to see that this actually works in reality. It would be great if something similar to what happened with gravitational waves occurred, where we managed to reconcile things in some way and at some point discovered a particular factor that behaves exactly as described in the mathematical model of the Grand Unified Theory. But for now, I repeat, there is no such theory, and I repeat, such a theory is not even on the horizon yet. Moreover, this theory is often approached, let's say, rather aggressively, and is regarded as something of a scientific meme. As one respected reader wrote in the comments, "Do you really believe in this scientific meme called the theory of everything?" There is a certain sound logic in this kind of nihilism. Perhaps we really don't need a theory of everything. Let me remind you that we are proceeding from a certain principle of similarity. We proceed from the idea that if we have a certain law of physics, it should work the same way everywhere. And of course, on the one hand, this is incredibly logical, but on the other hand, nothing prevents us from dividing worlds, so to speak, into clusters, with each world having its own mathematical formalism, its own mathematical model, and its own mathematical and subsequently physical approach that allows us to describe processes. So it turns out that quantum physics, as you remember, starts to work after a certain level, a certain size. Similarly, macrophysics stops working beyond that size. Or does it? Well, it doesn't completely stop working, but certain factors that we observe and so on cease to function. So, to say that one is completely inapplicable to the other would be incorrect. By the same logic, by the way, quantum physics stops working at macroscopic scales, or, again, doesn't work completely. And so the existence of a division of the world into certain fragments, into certain subworlds, can be quite logical. We can take a personal computer, which you are probably using right now, and on this personal computer, several programs can run simultaneously within one operating environment. One way or another, I think it's very appropriate to say just one thing about Einstein. Thanks to Einstein's gravity, quantum physics, which he initially supported, completely fell apart. And by and large, this process can be seen as a confrontation between classical physics and quantum physics. By and large, the whole problem can be described as follows. How did Einstein, using gravity, try to undermine the ideas of quantum physics? Whether we will find a theory of everything or not is a very debatable question. Whether we need this theory of everything or not, or whether the existing mechanisms are enough for us, is also a completely ambiguous question. Nevertheless, work in this direction is ongoing. It is interesting and at the very least useful to know that such an approach to perceiving reality exists.